However, the problem with fusion is getting those nuclei together requires very high temperature and pressure, and those kind of conditions are not easy to reproduce on Earth. But for example, in the sun's core, the main energy production method is nuclear fusion. Okay, but on Earth, in our nuclear reactors, how we harness energy is through nuclear fission. So the fission of the larger nuclei, which lie at the right hand side of this graph. Okay, so ultimately, in the nuclear processes in the stars, in the core of stars like the sun, you have fusion which is carried on over and over until finally iron is reached, because iron is the most stable. Once iron is reached, there is no more nuclear processes. So this is also a reason why iron is the most prevalent element in the universe. Okay. Now, a little bit of housekeeping with units. So we have this equation here, E equals mc squared. Okay. Now I want to see what's the corresponding energy for 1 atomic unit of mass. Okay. So what I'll do is I'll replace m over here with 1u, okay, multiplied with c squared. So this is going to be 1.66 times 10 to the power minus 27 times 3 times 10 to the power 8 square. Okay, and this answer is going to be in joules, because here this is in meters per second, this is in kilograms. Okay, now if I were to divide this, for example, by 1.6 times 10 to the power minus 19, I would get my answer in electron volts. Okay, so if you calculate this, the answer will be approximately 931.5 mega electron volts. Okay, so this means that the energy that corresponds to 1 U of mass is 931.5 mega electron volts. Okay, so this is a unit of energy. So you can also write it like this. Okay, so 1 U times c square is 931.5 mega electron volts. Again, this is a unit of energy. Now if I were to bring the c square on this side, that would mean 1 U equals 931.5 mega electron volts c minus square. Okay. This here is a unit of mass. Okay, this here is a unit of energy. So you must remember that 931.5 mega electron volts per c square is actually equal to one atomic mass unit, which is 1.66 times 10 to the power minus 27 kilograms. Okay, but if there is no c minus square there, we're talking about energy. All right, and this much energy corresponds to 1 atomic unit of mass. All right. So then we have some problem solving using mass defect and binding energy, where you should be able to use these kind of relations. Next part is fission and fusion. Like we just talked lightly about fission and fusion. Fission is when a heavier nucleus on the right side of the binding energy per nucleon graph splits into 2 daughter nuclei. Okay. Now the binding energy, the sum of the binding energy of the 2 daughter nuclei must be greater than the binding energy of the parent nucleus, because in any kind of a reaction you want to get into a more stable state. Okay, so a higher binding energy obviously means a more stable nucleus. Now that's fission. You can go into details over here. They should actually be familiar with a bit of fission. You can talk about how a chain reaction is carried out when one of the particles released in the reaction is actually what triggers the reaction. In the case of nuclear fission, it's always a neutron. Okay. Then you can talk about nuclear fusion. Nuclear fusion is when two light nuclei join into form a heavier one. Again, you want to talk about why this cannot be done on planet Earth, or rather why it's hard to replicate what happens in the sun's core on planet Earth. Then 7.3.9 is basically telling you what I just told you, that the total binding energy of the daughter nuclei, the sum of the binding energies of the fission nuclei must be greater than the nuclei on the left side. Okay, then we have 7.3.10, state that nuclear fusion is the main source of the sun's energy. We have that. Again, you can go into a little more detail with the process that exactly takes place, how two protons form a deuterium nucleus, and then that combines to form a hydrogen 3, and so on and so forth. Again, over here you can see that at the end of the reaction you have two protons released which are required to carry out the reaction in the first place. Okay, then there are a few problem solving questions on nuclear fission and fusion. So that's it. Some of the more important points I have covered here, and I think just going through some of the numericals should get the students more accustomed to solving these problems. Remember that whenever from a left hand side of an equation, okay, you go towards the right hand side, okay, and let's say there's a difference in energy. This energy is always manifested as the kinetic energy of the particles on the right hand side. Okay, so this energy is not something separate. It is always manifested as the kinetic energy of the constituent particles. Now, when you're talking about nuclear fission, you also want to talk about nuclear reactors and how this kinetic energy is controlled by control rods, and you want to talk about the moderator in a nuclear reactor. So go into details. They should be familiar about nuclear reactors, but you still want to go into details of how excess neutrons are captured, etc., to control the rate of reaction. So that should pretty much cover this portion. The rest of it is in the second half of the quantum chapter. So that's the HL portion.